limit camp. And congratulations to everyone to be here. And we are very excited to have a whole week of mathematics. And over the next few days, we'll have a series of talks by students and some professors. And we will assume the limit syllabus as a part of it, so like a prerequisite. And we are planning to record all the lectures, and we'll try to put it in YouTube, of course, after taking the speaker's permission. And if not put it into YouTube, we'll probably try to share it with you guys. So please keep an eye on the inbox because we'll also mail the meeting links. And we request all the participants to keep your microphones muted unless you have a question or something like that. And yeah, that's it more or less. We hope you'll enjoy this whole week. And so today we have the first talk by Dr. Shubhodip Mondal, and I would like to request Vikram to say a few words.
Thank you, Shubhodip. Good morning, everyone. On behalf of ISI Bangalore student, I welcome all the participants the first day of Limit Math Online Camp. I have great pleasure in welcoming Dr. Shubhodip. He completed his PMath and MMath from ISI Bangalore and obtained his PhD under the advisory of Professor Bhargav Bhatt from University of Michigan in 2022. After that, he had postdoctoral positions at Max Planck Institute and Institute of Advanced Studies at Princeton. He is now a postdoctoral fellow at University of British Columbia, Canada, and will be joining as assistant professor at Purdue University. Dr. Mondal had taught during his MMath and had been recipient of PC Punisher Gold Medal from Indian Statistical Institute. And also, he received several prestigious fellowships, including Rackham International Student Fellowship and Hindu and Gopal Prasad Fellowship by the University of Michigan. His research interests include arithmetic, algebraic geometry, and homotopy theory. With great honor, I welcome Dr. Mondal to introduce us on Weil conjectures.
Right. Yeah. So thank you very much for inviting me to give this talk. And yeah, I'm really happy to see all of you. And I guess many of you are students at ISA as well. And also thanks for the introduction. So yeah, so as you see, I think the title for my talk is Introduction to Weil conjectures. And so the topic kind of surrounding this is what's called algebraic geometry and also maybe arithmetic geometry. So my goal is to sort of give an introduction to the Weil conjectures. And I would like not to assume much about algebraic geometry. So I'm hoping that it would be okay if you don't know anything about algebraic geometry at all. And I think it would be enough if you know just what a polynomial is in kind of multivariables and also some basic kind of abstract algebra such as rings, fields, and so on. But of course, I think at some parts, maybe the things I'll be talking about, you might not necessarily know what they mean. So maybe just kind of take it as a story. And in the end, I'll also try to give some references. So, if any of these things kind of makes you want to learn more about this, you can go to these sources and learn more. Okay, so maybe I'll just start. So first, let me just very briefly say, vaguely as well, what is an algebraic variety? So algebraic varieties. So for this, we'll always fix a field. So let K be a field. And so for example, K could be Q, which is called the field of rational numbers. It could be R, field of real numbers. It could also be C, the field of complex numbers. But what would be most important for our talk here is that it could also be FP for some prime P, which is called the finite field with P elements. So it's just integers modulo P, and every element which is not zero has an inverse modulo P, which is what makes FP into a field. So when we are kind of talking about algebraic geometry, there are two examples of varieties that really play a very important role. one is called the affine space, affine n space. So this just means that you look at all n tuples, x1 to xn, coming from k to the n, where k is the field. So the affine space is actually, you can also say that it's just another name for the vector space k to the n. So it's just the n-dimensional vector space over k. And a related construction is what's called a projective space. And this we denote by Pn. So for this, what we do is, first we look at all n plus 1 tuples coming from k again, but we remove the origin. So we remove 0, 0, 0, 0. We would like to remove that point, and further we subject this to some equivalence relation. The equivalence relation is of the following form. So if you call this n plus 1 tuple, sorry, so if I write x0, this should just be xn. So if you call this x underline, so you'd say that x underline is equivalent to y underline if they differ by some non-zero constant. So again, this would not be that important for us to know what a projective space is. Most of the things that I'll be talking about, it will be phrased in terms of affine spaces only. But so the affine space and projective space, these are two sort of very kind of like the building block, really, in some sense, for algebraic geometry. So now let me say what is an algebraic variety. So in general, an algebraic varieties say over K are basically whatever subsets you can get either inside the affine space or inside the projective space that are cut out by solutions to some number of polynomial equations. So let me write that down. Locally given by a subset of some affine space, let's say, which satisfies some number of equations. And what are these FIs? These FIs are just polynomials defined over K in n variables. Okay, so let me quickly give an example of a variety. So inside the affine plane A2, you could look at the kind of the points which are solutions to an equation of this form, which is y square equal to some cubic equation, let's say. And this type of varieties, they have a name. They are what's called elliptic curves. Even though they're so easy to define, it still forms a very active area of research in math. Okay, so I have roughly introduced what an algebraic variety is. This is the solution sets to polynomial equations. And now I want to move to what was advertised in the abstract, that I'll be talking about the zeta functions in this context. For algebraic varieties. So the setup is that let X be an algebraic variety. And think of it in terms of polynomials, meaning you have some polynomials whose solution set defines the variety. And suppose that these polynomials are defined over Fp. So the field for now, and from now onwards actually, will be Fp, where P will be a fixed prime. So to define the zeta functions, I need to actually use more fields than just Fp, which is called the field extensions of Fp. So Fp is a finite field, and there are several other fields containing it, which are all finite fields. So just called Fp square, Fp cubed, and actually Fp to the k for every value of k. And these are fields whose size is p square. And so the size of Fp to the k is p to the k. Actually, there's a unique field up to isomorphism whose size is equal to p to the k. So just the property that its size is p to the k kind of defines it uniquely up to isomorphism. That one proves a posteriori. So these are all finite fields. And so the idea is that when you have such a variety given by this kind of equations, so you want to make the following definition. So you let nk to be the number of solutions of these equations of so all of these are polynomial equations defined over the field Fp, but it makes sense to try to solve them, to look for kind of solutions in fields that are larger than Fp. So in extensions of Fp, for example, Fp square, Fp cube, and so on. So we will let nk to be the number of solutions of this equation where the coordinates are allowed to come from Fp to the k. So not just from Fp, but from Fp to the k. And we can do this for every k greater than 1. So for any k greater or equal to 1, this is a construction that we can do. So now we are ready to define the zeta function. So first we define it in terms of some power series. So we define z x comma t to be the exponential of this infinite sum, k equal to 1 to infinity n sub k times t to the k over k. Okay, so this is a formal sum, and you can view it as a power series. And then you're taking exponential of a power series, and that's also well defined as a power series. So basically, the whole thing is a power series, which we denote as an element of this ring. So this is the power series ring. And so what's really called maybe the zeta function, which is just obtained from z by just this simple change of variable, really. So you let zeta of x comma s to be z x comma p to the minus s. So when I say zeta function, I kind of from time to time mean both of these, but it will be clear from the context which one we're actually talking about. So this is the definition of zeta function associated to an algebraic variety X. And before we kind of go forward with this and talk about more things, I want to explain the analogy of like the definition that I just gave with the classical Riemann zeta function, because the formulas, it doesn't exactly look similar. So I want to explain how to see this similarity. So the analogy with the Riemann zeta function. Okay, so zeta of S in a suitable range is defined as summation of 1 over n to the s from n equal to 1 to infinity. This is the kind of the definition of the classical Riemann zeta function. But the zeta function also admits a product formula that's called the Euler product formula. It says that zeta of s can be expressed as a product of this form. Product ranges over all primes P. So if you haven't seen this, you can kind of treat it as an exercise to try to prove. So this 1 over 1 minus some quantity, you can try to expand it as a geometric series, and then you can play around with it to see why it has to be the same as the other definition of the zeta function that I gave. Now, to explain the analogy that I'm about to explain, this Euler product kind of description of the Riemann zeta function will be really important. So let me go one step more with this. So imagine that there's an algebraic variety that X. So if you know some more advanced commutative algebra, this can be taken to be what's called spec Z, but we will not need it. So let me just try to draw a picture. So imagine X is some kind of algebraic variety which has 1 point for every prime. So you have X2, X3, X5, X7, and XP, one point for every prime. And so you can then think of the Euler product also in this way, where you're taking product, let's call this X, for every point in X, and then you have 1 over 1 minus 1 over but say I define the size of xi to be I for all prime psi. So this is just a different way to rewrite the same thing. So this one and this one is just the same thing written twice, really.
What is the mod doing here?
Sorry?
What is mod xi equals to I mean?
Yeah, so here I'm just defining it as some definition. So this mod, you can think of it as some kind of a size function, let's say. So just, this is by definition for me now.
Okay.
Yeah, yeah. So I think here this will be just an analogy. So for now, this is just a definition. Okay. So now let's go back to the case of an actual algebraic variety where you have some equations, really. Okay. So now let X be an algebraic variety defined over a finite field. fp. So for every point x, for every point little x in capital X, so one can define a size function. So here you can actually define it in a more meaningful way. One can define size of x as just, this is the symbol, but if you want to know what it actually means, it will take a little bit of work, but this will be the cardinality of the residue field at x. But for this, you would actually need to know a little bit more of algebraic geometry. So I'll not get more into that. But for every point, there is something called residue field, and you can just take the cardinality of the residue field. And that would be sort of the definition of the size. But for now, let's just assume that you know how to define it. But then one can prove, and I will not prove this, but sure you can find this somewhere online as well. So the zeta function, the way I define it, will admit some Euler product formula. Where this little x varies over points of the algebraic variety that we had. So this product formula is really the kind of the version that shows the analogy of our zeta function more clearly with the classical Riemann zeta function. So that was the analogy. It's not completely crazy or something. Yeah.
What was S on for here?
Sorry, I didn't.
What is S here? X
Oh,
comma S.
so s is the variable that I was using. You can take s to be say you can let it be kind of any complex number, but it might not be defined everywhere.
I see.
But I mean it to be like a function in complex variable for the parts where it's defined. Like for Riemann zeta function, this s can only be where the real part of s is greater than 1. So, but you should think of s as some complex number.
Okay.
Right. But for now, I think from now on, for the most part, actually, you can just think in terms of the formal variable t. Before I have I've done the substitution of t equals p to the minus. Let's just take it as a t to be a formal variable. Yeah. Okay, so I have made these definitions, and I want to do some examples before I even go further. So let's do some kind of calculations. So say I take x to be this affine space. So nk, this will be basically, so the affine line is just basically one coordinate, and that coordinate is coming from the field, whatever the field you're interested in. So this will just be x, such that x comes from the finite field fp to the k. And this size is just the same as the size of the finite field, which is equal to p to the k. Now we can write down the zeta function of the affine line A1. So let's use the definition. So it's exponential of summation n sub k is p to the k. So I'll just write it as p to the k times t to the k over k, k greater or equal to 1. And well, you can combine p and t together. Okay. And now let me remind you of this identity, which is the power series expansion for log. And I'm writing it slightly differently, but I'm sure you can all check this. So now if you use that here, the sum, you can rewrite that in terms of log. and this will be 1 over exponential of log of 1 minus pt. And exponential and log are inverse to each other. So it's 1 minus pt. So that's the calculation for the zeta function of the affine line. And I will do one more example. So,
Excuse me.
yeah.
So the variable here is t, right?
Yeah, the variable is t.
And the affine space here doesn't have a condition. So every solution is p to the k.
Right, right. I think a better way of saying is that you have p to the k number of solutions. Yeah.
Okay.
Right. Which is why n sub k is exactly equal to p to the k.
Yeah, got it. Thanks.
Okay, yeah. Right, exactly. So you don't have any condition. Yeah. So now let x be p1, the projective line. Now you'll have to go back into the definition of projective line for what I'm about to say, but there's some equivalence relation going on. If you walk through this equivalence relations, you'd see that P1 is actually affine line with a point added. And that point is often written as infinity. So P1 set theoretically would decompose into two parts. One is A1 and then a point at infinity, which we write as like that, A1 disjointing at infinity. So then if you wanted to find out n sub k, that would be the number of solutions A1 has for the finite field fp to the k. And as we saw, that number was just p to the k from before. But now you have to add 1 to account for the extra point at infinity. So this will be p to the k plus 1. And again, now you can plug in the value of n sub k as we did for the zeta function of a1, and you can work it out. I will just write down the final answer for this one. You'd see that this is 1 over 1 minus t times 1 minus pt. Okay. So one observation that I would like to make just from these two very simple examples is that a priori the way the zeta function was defined, it was a power series. Okay. But after you check the answers for the calculations we did, which are these two cases, you see that it's a rational function, which is to say that it's a quotient of two polynomials. So not every power series needs to be a rational function. For example, power series that defines exponential, that's not a rational function. The power series that defines logarithm, that's not a rational function. But kind of these two functions that we saw in these examples, they are quotient of two polynomials. So it's 1 over another polynomial in t, and that's what we call a rational function. So now I'm at a position where I can state some of the Weil conjectures that I wanted to mostly talk about. I will only be stating two of them and kind of focus more on them. So let me just state two of the Weil conjectures. This was proposed by Weil in 1949. And so I think this is almost the most influential conjectures in algebraic geometry. And they have both been proven, and I'll say a little bit more about that. So the setup is exactly as before. So let X be an algebraic variety over FP. So the first one says that after you have defined the zeta function, as we have, this is always a rational function. Just to say, the zeta of x comma t is p of t over q of t, where these are polynomials with coefficients in q, let's say. And the second one, I'd also like to state it, is that, so let's do the substitution again and think about zeta of x comma s. So this has all zeros and poles on the critical line real S equals k over 2 for k being a natural number. So this is what's called the analog of Riemann hypothesis. So it's not just about the critical line real S equal to half like the actual Riemann hypothesis, but it's real S equals k over 2 for all integers including 0. Sorry, for all non-negative integers.
Does this zeta function extend to the normal zeta function that we are used to?
No. So I think I was explaining this analogy here, that if you think in terms of the Euler product, then there is an Euler product kind of formula for the zeta function for the algebraic variety x. But for the other one, I was saying, imagine an algebraic variety x, but there is no such algebraic variety over finite field that will realize the picture. So this spec z, this is not defined over a finite field.
I see.
Yeah. So in this Weil conjectures, x is always over finite field, and by working over this kind of finite field fp, you can't actually realize the Riemann zeta function. So this number 2, it has no implications about the Riemann hypothesis. But it's definitely interesting, and it's a very interesting analogy. Okay, so let me do an example of the Weil conjectures before I just try to say some words about the proof of one of these. So I want to explain what kind of information can you really extract by, say, number 2 here. So this is what I will be doing. So as before, let E be an elliptic curve. So this would mean that it's given by solving some cubic equation where all of these coefficients are coming from Fp. So that's why I say that it's over Fp. So in this case, it takes some work, but one can work out the zeta function directly. So it would be 1 minus alpha t times 1 minus beta t divided by 1 minus t times 1 minus pt. Further, you have some relations between the alphas and betas. So alphas and betas are both complex numbers, but they're actually conjugate to each other. So that's something that one can say on this setup. And again, as you see, this like the zeta function is a rational function, as the first of the Weil conjecture says. But let me say something more about the second one, or what the second one says. So the second Weil conjectures, in this case, implies that the size or the absolute value. So here I actually mean the absolute value of inside complex numbers. So the absolute value of alpha will be p to the half. So this comes from the fact that I think the zeta function for the elliptic curve has some zero on the critical line half. That corresponds to the fact that absolute value of alpha as a complex number is p to the half. So this is implied by the second part of the Weil conjectures. So this is what Weil 2 says. Okay, but I want to show you some concrete implications of knowing the absolute value. So that will be in terms of the point counts. So we can again let nm be the number of kind of points or the solutions that this equation has over the finite field fp to the m, and then we'll see what we can say. So by definition, this will be log of the zeta function of e comma t. And if you expand this out using that log takes multiplication to addition and this kind of properties, you'd see that you can expand it, but also using the zeta function of p1. And now let's take the coefficients of t to the m on both sides. So on one side, you'd get nm over m. And on the other side, so you'll have to work this out, and I will just write down the calculations. And the main important thing is the final conclusion that I want to get. So I'll just write them down without explaining too much. So if you take the coefficients of t to the m, you'd get this number that I just writing. So you can, of course, cancel off the m, and then you'd get that. Okay, let me write it this way. Yeah, so nm minus p to the m minus 1 will be negative alpha to the m, negative beta to the n. So if you are interested in the absolute value, we just have to take the absolute value on both sides. But then if you use the triangle inequality, this will be less than or equal to absolute value of alpha to the m plus absolute value of beta to the m. But alpha and betas are conjugate to each other, like I said. So they have the same absolute value. So this number will be 2 times the absolute value of alpha to the m. But then I was just saying, absolute value of alpha is p to the half. So this will become 2 times p to the m over 2. But then if you combine the first line with the last line, quickly let me write it down, you get an inequality. So this gives you some bounds on the number of solutions that the elliptic curve has over the finite fields, fp to the m. So it gives some bounds. This is called the Hasse-Weil bound. Is Weil estimate for elliptic curves. And there's actually similar estimates that you could do for any curve, not just elliptic curves, but I'll not get into that. So in this case, we see that the Riemann hypothesis part of the Weil conjectures, which is proven, gives you some kind of bound on the number of solutions that the elliptic curve has. Okay, So then let me now get into let me get into a little bit of the history of these two Weil conjectures. So the first one, the rationality, was proven by Dwork in 1960s. And then later also by Grothendieck, who also proved, so this is along with some of the other conjectures, such as there's something called the functional equation that I didn't talk about, but it was also proven by Grothendieck at the same time. Now with some of the other conjectures in 1965, using this theory of the schemes, Hidalgo homology, Elatic homology, etc. And the second one, the analog of the Riemann hypothesis part, was proven later by Delhi. And this was in 1974. And this made a lot of use of Hidalgo homology. And yes, actually, Delling's proof, I think it's also regarded as one of the biggest achievements in modern algebraic geometry, which also maybe for the first time really showed the extreme power of these techniques like schemes, Hidalgo homology, Elatic homology, and so on. And so for the rest of my talk, I want to briefly sketch or explain the tools and the main ideas that go into the proof of the rationality in the lines of Grothendieck's proof. So, sketch of proof of the rationality of zeta function. So sort of the first step is to think of the number of solutions in a somewhat different manner involving the Frobenius map. Which is a very key ingredient when you are trying to study algebraic geometry over finite fields like FP. So for any algebraic variety, so for say algebraic variety X over FP, and as before, think of them as solutions to some equations. Now I want to make another definition, which we call X bar. So what X bar is you look at those solutions coming from not just FP or FP square or any of these things, but actually from the algebraic closure of FP, which is denoted as FP bar. So you're looking at solutions coming from FP bar. So that means points such that all these polynomials would vanish. You can think of it as solutions over FP bar. And so one of the really neat and
Sorry.
crucial, yeah, sorry.
Bar.
Yeah.
I could not hear. What was FP bar here?
Yeah, so FP bar is the algebraic closure of FP.
I see.
So if you want, you can think of it as a union of all the finite fields FP to the K as K gets larger and larger.
Okay.
Okay, so this is a very important observation. So which leads to the Frobenius map. So if you have a point of this form in X bar, then you could raise each of the coordinates to the pth power. And that would again be another point of X bar. So if you have one solution to all of these equations, then raising each of the coordinates to the pth power will give you another solution. And this essentially holds because of this identity that a plus b to the p is equal to a to the p plus b to the p in characteristic p. That's the basic reason. But once you have observed that, you could take any point and then send it to the other point where you have raised each of the coordinates to the pth power. And this gives a map, an endomorphism of x bar, which you denote as the Frobenius. So f x bar, x bar. So this is called the Frobenius map. So now, as I was saying, that we are looking at solutions coming from the algebraic closure, but we do want to understand the n sub case, the solutions over the finite fields coming from the solutions where the coordinates come from fp to the k. But there is a way to use the Frobenius now to actually get to that number. So for this, we use this kind of reconstruction of the finite field from the algebraic closure as follows. So fp to the k can be thought of as those elements of fp bar such that x to the p to the k is equal to x. And this one, you can also think of it as the kth iterate of the Frobenius. So another way to say this is you take the kth iterate of the Frobenius map, and then you get k again. Sorry, x again. Now, if you use this observation, you see that nk is the same as the cardinality of those points in X bar such that when you use the Frobenius map we defined and iterate it k times, the X bar that comes from the finite fields fp to the k must be a fixed point of this Frobenius map iterated by k. That's because, essentially because of the definition of the Frobenius map. So if you take the kth iteration of the Frobenius map, let's see what that would do. You basically raise all the coordinates to the p to the kth power. And if that has to be equal to the initial thing, that would imply that xi to the p to the k is equal to xi for all I between n and 1. And this will imply that xi, all the coordinates really, come from fp to the k. So the points that come from fp to the k can be thought of as fixed point of a suitable iterate of the Frobenius map. that's one of the key points here. And the other key point, as I was saying, is the notion of algebraic cohomology. So very briefly, what does algebraic cohomology do? So instead of working with rational numbers, we actually work with an extension of rational numbers, which is called the algebraic numbers. So I'll not define it, just kind of take it as a story if you don't know what it means. So this is the field of algebraic numbers. So if you have any algebraic variety, the theory of algebraic cohomology attaches certain vector spaces, kind of gives you some linear algebraic invariant. So this HIX, QL, this is basically just a finite dimensional QL vector space. And this works for all positive integers. Additionally, these groups HI, they become zero if I is bigger than the dimension of X. So for a fixed X, this is only actually, this is I is greater than 2 times the dimension of X. So it's a kind of a finite collection of finite dimensional vector spaces. And so this construction is what's called functorial in category theory, which means that whenever you have a map from X to Y, so whenever you have a map from X to Y, you get an induced map that goes the other way. HIY, QL to HIX, QL. In particular, we're just interested in applying this to the Frobenius map. So if you take the Frobenius map, F, that was a map from X to X, and then you have an induced map that we also denote as F, from HIX, QL to HIX, QL. So the very important ingredient in the proof of this rationality is what's called the Grothendieck-Lefsegg trace formula. So what it says is that the number nk, which is the number of fixed points of the Frobenius map, can be computed in terms of this algebraic cohomology group that I introduced. So the groups here are what's called algebraic cohomology groups. And the trace formula would say that you can compute this, you can compute the number of fixed points by a trace formula that looks like this. So you take -1 to the I, and then you take the trace of the kth iterate of the Frobenius acting on the vector space HI X, QL. So as I was saying, you have the Frobenius map, that's a map from X to X, that induces a map on algebraic cohomology for every I, and then you could take the trace of F to the K on this vector space, and then do an alternating sum. So I should say that this is an analog of what's called the Lefsegg fixed point theorem, or maybe, or I think maybe the Lefsegg-Hopf theorem from topology. So the idea that the number of fixed points can be computed in terms of some alternating crest formula. This was due to left edge, and it also appears as a left edge hop formula. In the Grothendieck left edge crest formula is an analog of the left edge fixed point theorem in the context of varieties defined over finite field, where you're also using L-aric cohomology. And if you apply this fixed point formula to the Frobenius map by the observations that we were making earlier, the number n sub k can be understood in terms of the L-aric cohomology groups. And another important observation is that this sum is a finite sum, because the groups involved here, hi, x, ql, which we're calling the L-aric cohomology groups, will be 0 for whenever I is greater than 2 times the dimension. So this is a finite sum.
I wanted to know what trace was here.
Yeah, so whenever you have a linear map, say T, from a finite dimensional vector space to itself, you can write it in the form of a matrix. And then you can add up the diagonals, and that's what's called a trace.
Okay, I see.
And the same thing can be done here, because f to the k, after all, is inducing a map from a vector space to itself. You can think of the map in terms of a matrix and then add the diagonals again. That would be your trace. Yeah. Okay. So in the remaining time I have, I will show you how the Grothendieck left edge trace formula kind of directly implies the rationality of the zeta function, where you have to use a little bit more of linear algebra and do a little bit of calculation. But this is something that can be done in the rest of the time we have. So this implies rationality of the zeta function. So let us see how. So you have zx comma t, that by definition is exponential of summation of n sub m t to the m by m greater or equal to 1. Now, this nk, or n sub m, that's just changing the indexing. N sub k has a different formula now by using the trace. And in the next step, I will be substituting that formula. So keep the m greater or equal to 1. For n sub m, I'll be substituting this formula. We have trace Frobenius to the m acting on hi x comma ql. And then you have t to the m over m, as we did. Okay. So you have substituted it. And now we can also switch the order of the summation. Okay, so one sum has m, other sum has I. There are two summations, so you can switch the order here. And keep the -1 to the I outside. And then inside, you have trace f to the m acting on hi x comma ql t to the m over m. So now exponential takes summations to product. So if you use that, this sum can be taken outside as a product. And also remember, I was saying that the dimensions, sorry, that hi x comma ql will be 0. if I is greater than 2 times the dimension. So using that, you can just write the sum to be from I equal to 0 to 2 times the dimension. So it's a finite sum, and you can take it outside as a finite product as well. And you have exponential. And then -1 to the I to account for the sign we have. Okay, so the whole thing you have here, so this is another fact from linear algebra that I'm using. You can write this as the determinant of identity minus t times the Frobenius map acting on hi x comma ql. So this is kind of like the characteristic polynomial, just a little bit different, where you send t to t inverse. So this is like the characteristic polynomial of any matrix. And then the signs are a little bit different, the -1 to the I+1, but I'll not say very much about this. Can ignore the signs for now. So the thing I want to say is that here, this is also a very general fact about linear algebra that you can try to prove as an exercise as well. So you have this f to the m acting on some vector space hi x comma ql. You can replace that by any vector space v. So if you have any operator f acting on any vector space v, you can take the trace of the action of f to the m on v, multiply that by t to the m over m, take a sum from m equal to 1 to infinity, and then take the exponential. You'd be able to simplify this using exponential and logarithm, like how we were doing before. And then you'd see that that would be directly related to the characteristic polynomial. So this comes from linear algebra. And you don't need anything about Ital cohomology or Elatic cohomology to do this step. This step is just linear algebra. But now if you look at this final expression, the characteristic polynomial is just a polynomial, and you have some alternating signs. So when you're taking the product, some of them are in the numerator, some of them are in the denominator. But most important thing is that this is a polynomial. And therefore, the whole thing is a rational function. And this is what that really ends the proof. So the main non-trivial ingredient was really the existence of Elatic cohomology and some of its expected properties, or like some very good properties, such as the Grothendieck-Lefsetz trace formula. And after that, when you play around and use some of the tools or facts from linear algebra, which are not the difficult part really, you directly get the proof of rationality. And you even get a formula for the zeta function, zx comma t, in terms of this very concrete product of the characteristic polynomials of the Frobenius action on this Elatic cohomology groups, which are also useful for many, many other purposes. Okay, so this is it. And as I said, I would leave some kind of further references where you can read more about this. So one such reference, if you're interested more in the elliptic curve part of the story, is the book of the arithmetic of elliptic curves, which is a book by Silverman. And another reference is Milne's lecture notes on Hidalgo homology, where you could read about how this Hidalgo homology is set up and so on. And for maybe the theory of schemes that are also kind of a prerequisite for Hidalgo homology, you also have Hartstrom's book on algebraic geometry, which introduces the theory of schemes as well. Okay, so I think this is all I wanted to say. So I will stop now, and thank you very much for your attention.
Thank you, Shubhodip, for this wonderful talk. And thank you everyone for participating. Is there any question? Maybe we can wait.
I wanted to ask something.
Yeah.
Can you scroll up?
Mm-hmm.
I wanted to ask, is the cohomology some kind of vector space related to X?
Yeah, exactly. Yeah. So this kind of like X will be like, if you give some algebraic variety X, this construction will give you kind of a collection of vector spaces. So you have H0x comma QL, H1x comma QL, and then HIX comma QL for any I. All of these are finite dimensional vector spaces.
Okay, so and L here is an independent variable. It doesn't depend on anything else.
No, yeah.
But-
So this L is some prime that you will choose. So I think you will fix this prime L for once and all, and then you will start talking about this theory of L-adic cohomology. But the L will be fixed. It doesn't depend on the variety or anything like that. No. Yeah.
Okay, thanks.
Yeah.
Is there anyone?
What's the difference between a classical Riemann hypothesis and analog with Riemann hypothesis?
So you're asking what's the difference between the classical Riemann hypothesis and the one I was doing today, the one for algebraic varieties?
Yes, yes.
Yeah. So I think the main difference is that well. So I think the classical Riemann hypothesis, if you look at the formula, I guess the main thing to say is that you can't get the classical Riemann hypothesis from the one for algebraic varieties of a finite field. So this algebraic, so the story for algebraic varieties is kind of like completely separate from the classical one. So I think there's some analogies between the two, but it's still completely separate.
Okay.
As in, there is no algebraic variety that you can apply what I'm talking about to say anything about the Riemann hypothesis. There's no algebraic variety. It's just impossible.
It kind of feels like the Riemann hypothesis for finite fields.
The Riemann hypothesis for finite fields.
No, I mean, if we were to look at finite fields and were to define a Riemann hypothesis, that it kind of is like that.
So here maybe I should say that the main thing is that if you look at the Euler product formula for the zeta function, it takes all the primes p. So this p can be any prime. But here you are just taking things that are points of the variety. So if you do it for spec z, for example, where maybe you can think of the points to be primes, then the Riemann zeta function for spec z will look like the actual Riemann zeta function here. But if you were to talk about the Riemann zeta function for spec z, the Weil conjectures don't say anything about that, because spec z would not be a variety over fp. So here, this assumption that you're walking over FP is very important. Because you're walking over FP, this 1 and 2, they don't say anything about the classical Riemann zeta function.
Can you for once show how the second conjecture implies the modulus to be 1, p over 2, p over this thing is?
Oh, yeah, right. So I think the calculation is like this. So I think you have to do some algebra here, but wait, just give me a second. Right. So this alpha, if you see, this alpha is a root of the zeta function. So sorry, I think 1 over alpha is a root of the zeta function e comma t. And so I think there is some change of variable involved. So you have to let t to be p to the minus s. And then if you do this kind of change of variable, then think p to the s will have to be equal to alpha. So if s is a root of the zeta function, then you'll have something like p to the s will be equal to alpha. So if you take the Riemann zeta function, zeta of x comma s, and if you take a root of that, then the relation of alpha as in here and the 0s will be of this form, that p to the s will be equal to alpha. Now if you try to take the absolute value of alpha, the absolute value of alpha will be absolute value of p to the s, and p to the s can be written as p to the real part of, sorry, if you take the absolute value of p to the s, it would just directly be p to the real part of s, because the imaginary part will be of the form p to the ix, that will have absolute value 1. And now if real part of s is equal to half, this will become p to the half. So you have to play around with this change of variable, and basically that would be it.
Yeah, okay, got it. Because you have to separate the real part in the complex, right?
Exactly.
Okay, got it.
Yeah.
Could you state the general result of linear algebra you were talking about, the trace indeterminate relation?
Yeah, could you say your question once again? Sorry.
Could you repeat the general result
Yeah,
of linear
yeah,
algebra?
yes, I can do that. Yeah. Right. So let V be a finite dimensional vector space. Over any field K, then you could look at the trace, sorry, and you also take a linear map, T, then you could take T to the M acting on V. You can take the trace of that. Okay, actually denoted by something else, it would be better. The linear transformation, let me denote it by, I don't know, S maybe. Do S to the M. And then multiply this number with T to the M over M. Summation from M greater equal to 1 to and then take exponential of that. So this is a power series. And this will be equal to, I think, the determinant of identity minus S times the variable T. So this S times T should be thought of as this kind of characteristic polynomial type of things. And I think there is a sign here. I think maybe this is 1 over that now.
Okay, thank you.
Yeah, I think it's 1 over. If I think it would be easiest if you just take V to be one-dimensional vector space from K to K. Like I'm just doing an example, and then take some multiplication by something. Maybe let S will be, say, multiplication. Sx will be, say, lambda x. And then let's try to see what this will do. So trace of S to the M acting on V, this will simply be lambda to the M, right? Because when you take the composition, you get lambda to the M. So the sum I'm giving you is lambda to the M times T to the M over M, and then the exponential. And this is exponential of negative log 1 minus lambda t. Okay, so this is the path series of log that I'm using once again. And this will become 1 over 1 minus lambda t. But then if you think about it, this is again just nothing but the determinant of identity minus S times t. So I was just doing the one-dimensional case, but this is the general form. And basically by doing what I just said, you could prove it in the diagonalizable case already. Like if V is a diagonalizable matrix, then the same proof that I just did will also imply that case. And the general case is similar. Maybe you can make it into the triangular form or something like that, and then you can prove it.
Yeah.
But this was used here.
I had a question.
Yep.
So is there some sort of connection of the zeta function you define for a variety with the zeta function for a number field, the Dedekind zeta function?
Yeah, so again, I think the variety one is not, sorry, I think when I'm working over a finite field, it will not be directly related to the, I think the number field one. And actually a number field one is a generalization of the classical zeta function as well. I think the classical zeta function is for Q, and the one you're talking about is even more general for some number field. And so the number field case is different from the one over finite fields, which is often called the function field case. So yeah, it's different. There's some analogy, but it's different.
Okay.
Okay. Is there any other question? Really, we can wait 1 minute, then we end this session. Thank you, Shubhodip, for
Thank you. Yeah. Hope all of you enjoy the rest of the camp and the other talks.
Yeah. Maybe we'll end it here. The next talk will start at 12.
Yeah.
Bye.
Bye.
For the participant, the next talk will start at 12. Please join the link that we have sent by email. Thank you.